So let's look at the homework for today. Everybody get it done?
Yeah.
No?
I don't know.
Almost. Well, kind of. The
last
last one I wasn't quite sure if I got the correct answer.
I think the last one was the most poorly. Yeah, it was like the most poorly worded question.
A lot of them were very interpretable.
Really?
Yeah. And like the output that they gave you.
How bad was it, Nick? How bad was the
I,
homework?
I don't get his
Did you get
answer to his input in the context of the question.
No.
So you got something
I
done.
didn't.
I think it's either wrong or.
All right. So let's look at this.
Then they
Is
aren't
it
describing it
incorrect
very well.
Red or
The root of red. So the first, the highest one up.
All right. So what was the 131? This guy? So the first one, 131?
Yeah.
All right, so write the following procedures for calculating on a binary tree. So definition is 1.1.7. So let's go see what this dude looks like.
It's saying a bin tree is either.
It's right by there.
You can search 1.1.7.
You're not gonna. Yeah, you're not.
Boom. All right, so it's a bin tree is either an int or it's a list containing a symbol followed by a bin tree and followed by a bin tree. All right, fair enough. Steal this real quick.
Get more diarrhea for Evan's butt.
All right. So, let's see. So write the following for that guy. So leaf and interior node, which builds bin trees. Then we should also have a leaf predicate. What's a predicate? Function that takes a single parameter, boils down to true or false, which tests whether a bin tree is a leaf. And lson and rson and contents of, which extracts the components of a node. Contents of should work on both leaves and interior nodes. Okay, so lson, what should this guy do?
I think it finds the left.
It's the left son from the interior node or whatever.
Yeah. It just takes the.
So an interior node it should give you this guy. Rson it should give you this guy.
Correct.
All right, and then contents of would give you this.
Yep.
All right.
Or the leaf number, depending on where you're at.
Or the leaf number.
Because a bin tree can just be an int.
Oh, I gotcha. So if it was, well,
Right.
so if it was one of these guys, if this was the bin tree you were operating on, the value would be this guy.
Yeah.
Okay. So depending on whether we're dealing with a leaf or we're dealing with an interior node. Okay, got it. So we need to go ahead and write some stuff. So the first thing we're going to write is leaf and interior node. And leaf, to create a leaf, we have what? Just an integer? That's our constructor for leaf. It's just taking in an integer. So we're going to define leaf to be a lambda that takes in a num and ultimately returns a list containing the word leaf.
Just num. Literally just output num.
No,
just
num.
literally num. No list.
Because it's
It literally just is a wrapper.
It's literally nothing but.
Hold on. Leaf looks like this.
Yeah.
So that means you're calling upon leaf and then
That's how you would
Setting
build.
it.
Oh, that's how you, so you would build a leaf by calling the leaf function on this integer.
Yeah.
Okay, so it just takes in that and boils down to the number.
Yeah.
All right, so like that.
Literally useless, but yes.
All right. So, well, except we get to now call it leaf as opposed to interior node. So then define interior node. Interior node to be a lambda, and this guy should take in a bin tree. Well, no, it should take in a val And 2 trees?
Yeah.
Okay. So now we're gonna have to define what trees are in this as well, right? So if I write this generically, we're gonna say this guy takes in a val, a B tree, let's see, B1 and a B2.
Would it be easier just to put left on and then right on? Because
Would that make you happier?
well, I mean, it just makes
L-son, R-son?
Yeah.
What does R-son even stand for?
Like
Right
kids.
son of.
Oh, right son, like child?
Right son.
Child.
Left son and right son?
Yeah.
Oh, that's stupid.
Trust me.
Okay.
Gets
All right.
stupider.
So define interior node is going to take in 3 values, a lambda, a left side, and a right side, and both of these are binary trees, right? And then it's going to boil down to a list containing those 3.
Yes.
So a list containing val, L-son, R-son. So we just created a bunch of constructors. Well, 2 constructors, not a bunch. 2 constructors. All right, so now we can generate leafs and we can generate interior nodes. All right, now what are we supposed to do next? All right, so those 2 guys build binary trees. So let's just test those real quick. So I should be able to build an interior, I don't like that word, interior
Change it.
node, passing it blah, and then passing it a, let's just do 2 leaves.
Yeah, use that constructor.
Leaf 5, leaf 6, like that. And there's our blah 5, 6. That's an interior node, so we're good? All right. Okay, so now we're supposed to write a predicate called leaf, which just tests whether a particular binary tree is a leaf. Okay, so we're going to define leaf to be a lambda that's going to take in a B tree, and it's going to return true if that B tree is a leaf and false otherwise, right? Now we know that all B trees will be a list containing at least one thing.
Val list.
Oh, we just need to ask if it's a number. Okay, so the leaf is not a list. The leaf will just be a number. So really we're just asking, we're just going to return number of B tree. Like that. So that's leaf. All right, so our B trees come in 2 forms. It either comes as just a number or it comes in the form of a list containing a value in 2 B trees. Fair enough. All right, so here's our predicate for leaf. Allows us to ask if a particular B tree, which I'm guessing later on we're going to ask if a particular L-son or a right-son is a leaf or is not a leaf, which means it must be an interior node. Okay, so we got that. And then we need L-son, R-son, and contents of. So L-son is going to return the left son of a B tree. Okay. So define L-son to be a lambda that's going to take in a B tree as a parameter. And so we can't, do we need to check?
No, you can just straight.
We could just return the left sign. Okay, so it's going to look like something like this. So if we want the left sign, that's going to be the car of the cutter, so the catter, right? So this guy will just boil down to the catter of B tree. And then define R-son to be a lambda, takes in a B tree. And this guy's going to return the catter of B tree. Did I pronounce that right? The cadder of B tree. So far, so good? All right. Then we're supposed to get contents of that just returns the first part. The car. Or if it's a leaf, the number. Okay. So define contents of. Purpose of this assignment, for those of you who are interested, drill binary trees a little bit anyways, but regardless of that, this idea of building constructors for sub-objects, because as we start getting into our language building stuff, Right now we're building the language of binary trees. As we get into our language building stuff, we're going to be building constructors, which end up just being wrappers for stuff. So it's kind of getting us into that mode of dealing with things like that. Okay, so there was a little bit of a rhyme or reason. I'm not sure, I haven't looked at them, but there isn't really possibly a rhyme or reason to the 3 3-star questions I gave you for Tuesday, other than it sounds like it'd be a really fun assignment. Does it? Let's just finish this one real quick and let's take a peek. I usually don't look at these till we come to class because that way I'm entertained. Contents of needs to ask the question. So if, oh, thank you. Lambda, B tree, then if, or do you want to use cond? If's pretty, this one's pretty short. This one's pretty short. So if number, oh, yeah. Perfect, very nice. If leaf, so he's using our predicate that we built. If leaf B tree, if it's one of those guys, then we're just going to return B tree. Otherwise, we're going to return the value, so the car of B tree, like that, right? So is that it for the first part? Number 1. Okay, that was okay. So we're done with 3-1. All right, built all the pieces, perfect, amazing. All right. 3-2, write a procedure called double tree that takes a bin tree as represented, blah, 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 and produces another bin tree like the original, but with all the integers in the leaves doubled. Okay, so we're going to walk through, and we're going to take a B tree, we're going to walk through that B tree, wherever it's a leaf, we're going to boil down to double that, right? We're going to construct a leaf that is whatever the current leaf is, doubled. Otherwise, we're just going to keep what's already there. So this is really a tree traversal question. The name of it is double tree. All right, so define double tree to be a lambda that takes in a B tree. Brett. We've never had a, oh, we did. We had a Brett Hansen in class. You guys ever know Brett Hansen? Brett was a good guy. Looked a little bit like a vampire, but actually, yes. I don't remember what. Maybe it was just vampire. He gave it to himself. He worked for Awesome Fat for a long time. Let's see. Define double tree to be a lambda takes in a B tree. So what we're going to go through is anytime it's an interior node, we're just going to leave it alone. Return that, right? Okay. Whenever it's a leaf, we're going to return that leaf plot. Well, actually, whenever it's an interior node, we're going to call double tree on that interior node. Whenever it's a leaf, we're going to double that guy. Correct? So let's start asking some questions. So we'll ask an if. So if leaf B tree, then what are we going to do? We're going to multiply, so times B tree, or is it just times 2? Yep. Not squaring it, okay. So B tree times 2. That's what this guy will boil down to.
If you really want to follow the pattern, you can use the contents of.
Oh, that.
Contents of tree times 2 in that B tree.
Oh, I do like that. I do like that to kind of keep going. So if leaf, okay, yeah. Yeah, but is that
you
kind
can use it in the second one.
Yeah, the second one makes more sense. So if we're looking at a B tree, yeah, we should use it as the second one. Yeah. So if we're looking at a leaf, if our whole tree is just a leaf, then we're going to, otherwise we lose the ability, we have to check for number. Then we'll return whatever the thing is times 2. Otherwise, actually, we don't even need to do concept stuff.
No, you don't need to.
Yeah. Otherwise, we just call double tree. Actually, no. Let's see. Otherwise, oh, we would. Otherwise, we will boil down to B tree. Yeah. So we're going to build an interior node, passing it B tree. Well, passing it the contents of val, or sorry, was it just contents of that, which will give us the car, correct? And then call our recursive function on arson and lson and arson. All right, so interior node passing it contents of B tree along with double tree on, is it lson first? Lson B tree and arson B tree. Oh, double tree again. Yep. Double tree just takes in a single B tree. Well, let me kick this down the line. It's going to start getting messy. Double tree. Arson. B tree. That should be double tree. So double tree takes in a binary tree. If the binary tree that this particular call to double tree received is just a leaf, then we're going to return whatever that leaf is doubled. Okay? Realistically, we probably should use our constructor, our leaf constructor up here, right? With the double number to follow the pattern technically.
A lot of things that you could.
So really, if we want to be totally legit here, we would say leaf this.
You take the times contents of 2 or the tree.
Yeah.
Well, do what you want.
I don't think that's better. I think this is better. All right, so we'll construct a leaf out of what the hell? Construct a leaf out of the contents of that particular B tree, which is just going to be a number, right? Times 2, and we're going to construct a brand new leaf out of that. All right, so there's our leaf constructor in action, using our contents of extractor there, whatever. But we know this guy's going to ultimately boil down to a number because we wouldn't be here if we weren't dealing with a leaf. And contents of always returns a number when we're dealing with a leaf. Right? All right. So if I'm just dealing with a leaf, return a new leaf that is double the value of the contents of the old leaf. All right. Otherwise, I'm going to call interior. I'm going to build an interior node. We're constructing an interior node. An interior node takes what as a parameter? We take a value, a left tree, and a right tree. Those are our parameters to construct an interior node. So this interior node is going to take in the value of this B tree, that's the val, along with whatever double tree returns, so this function called recursively, on the left child, and whatever double tree returns, we're calling recursively on the right child. Make sense? All right, so that's double tree. So is that all we have to do with 132? All right. 133, write a procedure. Mark leaves with red depth. Oh, that's a mouthful. That one. I mean, that's not even a fair function name. All right. That takes a binary tree and produces a binary tree of the same shape as the original, except that in the new tree, each leaf contains the integer of nodes between it and the root that contain the symbol red. All right. So, for example, here's a leaf. What was this? This is the output?
Yes.
Okay. So, for example, we hit a leaf right here. So this is bar. Bar has 2 leaves. Leaf 1, leaf 2. That's these 2 guys. So now our interior node, so anytime we see an interior node, we're going to replace it with kind of a, didn't we have an assignment on lexical address at some point? Or not yet? That one's coming? Okay. So we're going to replace interior nodes with this kind of format, right? That is the contents of the interior node followed by the number of reds found between the left child and the root, and the number of reds found between the right child and the root. Does that sound right? So if we look at this guy here, as we're walking down here, we have our top level interior node, red. So I'm going to keep a running count. I'm at 1. I'm at 1 right now. Okay. Then we get to our interior node. The second I hit an interior node, I know I'm doing some new formatting stuff. Interior nodes get reformatted like this. Okay, so I'll be building a list. The first element of the list will be the contents of that interior node. Every time, right? Notice I have my variable here with my 1. Okay, that's the number of reds I've bumped into so far. Then I hit my left child. In this case, my left child happens to be a leaf. Therefore, I can go ahead and give him the current value of reds that I found so far, which will be 1. Then I get to my right child. My right child also happens to be a leaf, so I can give him the current value of the reds I found before. No more recursive calls is what I'm getting at. All right, then I'm done. That was our call to the left child of our original interior node. Now we're going to call the right child of our original interior node. Notice that we still have red as 1. That's our count. All right, so this interior node has a value of red. Count just went to 2. Okay, so that's the +1. We're going to have a recursive +1s. So now that guy's 2. So I go to his left child. His left child is a leaf, therefore I'll boil down to 2. It should be, yep. So here's, name of it is red. Left child is going to have a value of 2, the number of reds found so far. All right. Then we have his right child. This is his right child. His right child is an interior node. What do we do with interior nodes? We replace them with this new format. The new format says create a list containing the contents of and the number of reds for each of the left and right childs, right? The number of marked leaves, blah, blah, blah. All right, so this guy, that's our leaf. He'll have a depth of, well, not I say depth, that's our lexical address stuff. So this version of an interior node will be replaced with the list containing the contents of that guy, as well as, since this guy's a leaf, the left son is a leaf. And since he's a leaf, we get our current value of number of reds, which will be 2. And since this guy's a leaf, we'll get our current value of number of reds, which is also a 2. Okay, then we stop calling stuff, which then allows this guy to stop calling stuff, which that's where we get this finished thing here, which then allows the final thing to be done. Make sense? All right, so does it make sense what we're trying to accomplish here? The impression I get was this one was hard to understand. Does it make more sense now that I've explained it? Now, I think I saw David posted something up there that's translated this from hieroglyphics to this.
Not this one. This one.
Which one? The first one?
The definition of
Yeah, the
binary
definition,
tree.
because people were.
Oh, I got it. This one, because you didn't have that context that you were building a bunch of constructors,
Right.
it read funny?
Yeah.
Okay. Does it read better now that I put it in that context?
Yeah, I was still completely off base with content stuff. But
Okay. So I probably should have given you that context beforehand, but it may have been less fun.
yeah, fun. That's the word we were all using.
Really? I didn't get any pictures of tears or anything. I've still been promised.
No, because we had our translator.
Oh, translators.
Once the translator came through, it's fine.
I've been waiting for Levi's promise me as a bucket of tears in storage somewhere. Maybe it's a midterm type of collection urn. That actually would be really, really funny if you kept it in like an environment that didn't allow any moisture to escape, and it literally was a collection of tears from this.
Every night I'd cry into it. For however hard I thought that
You
was.
gotta take a video of it.
The amount of extra credit is just astronomical. If you could prove that was the source. It's just so good.
Videotape it every night. As you just try
All
and
right,
build up.
so let's write this guy. So Mark leaves with. Man, I don't like the name of that. I'm gonna have to write that. Oh my gosh. Okay.
I just use the first letter of each.
MLWRD.
Yeah.
That's not what the cool kids would do.
Call it red.
All right, no, we're writing the whole thing. So we're gonna define. I've copied it, so now I don't have to worry. Boom. Okay, nailed it. So we're gonna define that to be a lambda. To be a lambda.
You're gonna define what to be a lambda?
Who?
What are you gonna define to be a lambda?
Mark leaves with red depth.
Okay.
To be a lambda. And this guy is going to take in. We need a helper function because we need to have a count.
Yes. Yeah.
We need to have a count.
No cheating.
With our current toolbox, it would appear we need to do that.
All right, relax. Okay, so this guy's going to take in a B tree.
Yep.
All right, and ultimately he's going to return whatever MLWRD.
Or you can just call it, traverse and be a rational human being.
MLWRD, passing it the B tree, and also passing it a 0 as our starting point because we've run into 0 reds at that point, right? All right, so now we need to define MLWRD. We're going to go ahead and copy that to be a lambda that takes in a B tree and a num. Well, let's do count. Count sounds better. So B tree and count. And this guy is going to ultimately go through our tree. Anytime we see a leaf, it's going to boil down to the count, and whatever you called it in yours, right? All right, so we know we're dealing with a B tree. So B tree is going to come in 2 forms. So if leaf contents of B tree. Actually, no, we don't need to do that. If leaf B tree, like that. Okay, so if leaf, that's what we did up here, right? We matched it. Okay, yeah, I just want to make sure we're consistent. So if leaf B tree, then what we're going to do is we're going to boil down to count. Right? And it's not a new leaf or anything. It's our new format. Okay, it's our new format we're creating.
Yeah, but you gotta leaf it.
No,
Yeah, you gotta leaf count.
no, this isn't. Does this look like leaf to you?
Yes.
Yeah.
Those are
That is a
beaches.
leaf.
Oh, this is still a B tree?
Yeah.
Does it say it should be a B tree?
It replaces leaves with.
I mean, that's like the output. So
A
if you
B tree
print a
could
B
be an
tree, that's what it would
Yeah,
be.
you create a new B tree in the same shape as the original.
Except that in the new tree, each leaf contains the integer of.
Does it say replace the leaf? I mean, at the end of the day, those are identical, so it doesn't matter. The new tree. Each leaf contains the integer. Oh, each leaf contains. Yep, you're right. You're right. It's a leaf. Each leaf contains. So this guy's not going to be that. It's going to be this.
Yeah.
Leaf count. All right. So we've replaced this leaf with the leaf version of count rather than the value that used to be there. Right? Okay, fair enough. If it's not a leaf, then it must be the other guy. And what does the other guy boil down to? So this guy here, you're saying is an interior node. Okay, it's an interior node containing contents of, as well as MLWRD of RSON or LSON with count plus 1. And the same thing for RSON with count plus 1. Okay.
You have to do another if statement.
No, you're good.
Why? No, if it's not a leaf, it must be an interior node.
Yeah. Well, you have to check what the value of the interior node is.
Why?
You
Because
can
if it's
check
red.
Yeah, you can check the content.
Oh, whether or not you need to add 1 to it.
Yeah.
Okay, right. So, We only add one if we have another red, if we found a red. Makes sense. So if contents, is it contents of? B tree, if this guy is EQ red, so we found a red, then we're going to go ahead and we're going to create an interior node, passing it contents of, I guess we'll just do a bunch of copies and pastes, pastes, whatever. Interior node, contents of B tree, along with ML passing it LSON of B tree, as well as plus count 1. And then let me steal this. And let's kick this down a line. So we're going to build our interior node out of this guy, and this guy. And this is going to be RSON B tree count plus 1. That's what we do if we found a red. If we didn't find a red, then we're going to build an interior node out of just count. Should do it. All right, so let's test this awesomeness.
You're gonna have to do a lot of work to get that to work.
Because I have to change all the.
And they didn't finish the parentheses on the end.
Oh, really?
I don't know why.
So left it as an exercise for the reader. Durr.
Something like that.
All right, Mark. Did I name it the same? Okay, sweet. Interior node. Boom. It didn't seem like that much work.
It was a lot of work.
A list red bar 1 1, list red 2, list q blah blah 2 2. Is that the right output? All right. So, is that everything we're supposed to do? Wasn't so bad.
Oh, the code wasn't bad. It was just,
Figuring out the question.
yeah.
I don't know, it didn't seem that hard to understand.
You were gonna make Leaf with a list, okay? I spent an hour down that rabbit.
Oh, I got you. So, I mean, I get it. I would have certainly figured it out. But the point is that you went down that rabbit hole till you realize what they actually meant.
Yeah,
I get it.
multiple times.
I get it.
There's also nothing in the book that references like 1.1.7.
Yeah, there is.
Sure it is. I searched for it. Look at this. 1.1.7. Then I'm going to do this. Look at this. Boom. Definition 1.1.7.
Grammar.
Even in our slides on binary trees.
It was like right past where you thought it would be if you were going backwards.
I may not have found it either, but Abe told me to search. Right? That was you, Abe?
Like
Impressive.
you would think it would be between 1.1 and 6 and I thought.
Do you even have grammar for binary trees?
Yeah, we did that.
Doesn't matter anyways. It's in the
All right.
slides.
Shut up! So let's keep going with new content. So we have stuff we can keep talking about. That's our binary tree
Oh,
stuff.
you're still way back.
Am I? I need to get to occurs free. No, we're good.
Third, fine.
We're good.
No, that's still way back too.
Oh, I want to start talking about occurs free stuff.
Oh,
We'll just keep
never
cooking.
Okay.
No, we're done with the homework, right?
Yeah.
So we're on to new stuff. Good. Yeah, I'm going to start because we're going to evolve this. Yeah, no, we're legit. Okay, so as a reminder, the grammar we're dealing with here is our lambda calculus grammar, where lambda calculus expression is either just an identifier or it's a list containing the word lambda followed by a list containing a single identifier followed by a lambda calculus expression. or it's a list containing 2 lambda calculus expressions, a 2 list. Okay. Let's see. So I want to write occurs free here. So we had a quiz not that long ago, because we haven't written occurs free. We've just talked about occurs free, correct? Okay, so we had a quiz not that long ago that dealt with, I gave you a lambda calculus expression and asked you if, tell me everything that occurs free, or asked you if such and such occurs free, something like that, right?
You just said define occurs free, basically.
Okay, what does it mean for, oh yeah, what does it mean for a variable to occur free in a lambda calculus expression? All right, so here they've said, here's the rules. If the expression E, well, I don't want to read the stupid rules, those are dumb. So a symbol occurs free in a lambda calculus expression if it is not bound in the same scope by the identifier in production number 2 of our lambda calculus expressions. So this is where variables get bound. Think of this as a function in our modern languages. Okay? Variables get bound in the parameter list of our functions. Right? Just like when I write a function in Java that takes an int a as a parameter, a becomes a local bound variable of that function. Correct? All right, so same thing's true here. Here's my function. Here's the parameter list of my function. Maybe the int a lives in here. So that means anywhere in here, that is the scope bound by this environment, by that local environment. Any use of whatever this identifier is inside of this lambda calculus expression would occur bound, because it's bound by this guy right here. Make sense? So this is really an exercise in scoping, and how we can have scopes inside of scopes inside of scopes. When we think about a Java program, at the very top you have your global variables, right? So right inside the class you might have 3 or 4 variables, and those are accessible anywhere inside the class. Even if you have 5 separate methods in the class, you can have those variables are accessible in any of those 5 methods, because those 5 methods live within that outer scope. Make sense? All right. But if you have a local variable in one method, it is not accessible in one of your other methods, because those guys have their own individual scopes and those don't cross over. Make sense? So I want you to think about this in our terms as this is a local variable scope environment, and this is the scope that exists within that environment that may also exist within a larger environment. All right? So what we want to do here is we want to write a function like this, like occurs free, that takes in a symbol and a lambda calculus expression, something that fulfills this grammar. And it returns true if this symbol occurs free anywhere in this lambda calculus expression, and false otherwise. Make sense what we're trying to do? All right, so let's go in here and write this and get rid of this crap. All right, so we're going to define occurs free to be a lambda that's going to take in 2 things. It's going to take in a symbol and a LCE, lambda calculus expression. Fair enough? Something along those lines. All right, and we want this to return true if S occurs free in the lambda calculus expression. Now, last time we introduced the idea of cond. And one of the things I advertised about cond is that it allows us to almost implement individual productions of a grammar. Okay? So we're going to write we're going to write a cond here to deal with the various pieces. So there are 3 different productions for our lambda calculus expressions. One of them is just an identifier, right? Just an identifier. How would we determine if something is just an identifier? What predicate do we use to determine if something is an identifier?
Would simple work?
Simple would work. Yep. So we're going to do a cond we'll say symbol LCE. If that's the predicate we're dealing with, then we're going to return true. Why did I return true there?
Because no matter what it's going to be, there's no, it's going to occur free because there's nothing, it's the first definition, I should say.
Okay, so something I want to bring attention to here, and it's something that's going to help some of you that are still having trouble in the whole recursion world. When I'm returning true right here, it's because in my little world, I believe and I realize that I might be one of 50 recursive calls to this occurs free here, okay? But from my point of view, this particular call to occurs free, if LCE is a symbol, that guy's a symbol, by definition, S would occur free, unless, what? Well, first of all, doesn't S have to occur? So it's only going to return true if S and LCE are the same. If they're the same, it has to occur first. So if I'm trying to determine if X occurs free in this lambda calculus expression, okay, so in this case, the variable S would be equal to X. And LCE, in this case, let's say it's just an identifier. If that identifier is X, then indeed the symbol X occurs. And as far as my little world right here is concerned, it occurs free. Because I am not aware of any binding in my little miniature world right here. There might be an exterior binding that one of the previous recursive calls knows about. Okay, I'm just one little cog in the solution. Make sense? I can only answer the question here in terms of what I personally know. This particular call through here. So I'm only going to return true if first S occurs. So what I'm actually going to do is I'm going to return EQ S LCE. If S and the identifier, the symbol that is LCE, are the same, then that means S occurs, and as far as I'm concerned, it occurs free. It is not bound in my miniature world here. Make sense? And the reason I bring this up is, remember in your book it talks about breaking problems down to their little mini, smaller pieces. Okay? If you try to conceive all these recursive calls at once inside your head, you're going to get brain damage real quick. Real quick. All right? Always answer the questions in terms of what you know at that exact moment. The little piece of the pie we're looking at. Okay, so if I give us just an example of that here real quick, I might be looking at, let's say I'm looking for the variable x inside of the lambda calculus expression that is x. So S is equal to that, LCE is equal to that in this little version. Okay, so in terms of this particular call to occurs free, this is all of my given information. I do not know what's happening outside of here. This is all I have. So I'm going to ask myself, does this symbol occur in this lambda calculus expression? It does. Does it occur free? Well, since it occurs, because I see nothing about binding, because variables can only be bound in our second production of the lambda calculus expression with that parameter list. So since I'm not even dealing with that second production, it is impossible for anything to be bound in this little world right here. And I'm going to leave another version of the call to occurs free to possibly override me, veto my vote here of true or false. Make sense? Break it down into small little problems.
Is equal EQ going to work?
Yeah.
Because the way I understood it is that unless you define S as LCE, it won't work, even if it's the same thing. I thought you had to use equal for that kind of.
I don't think so. I think it should work.
Okay.
Yeah, equal only is used for like comparing bone structure of lists. I think it should be fine. The real question is it wouldn't be equal. The question is whether it's EQV. But I think EQ works fine for this. These are literals. EQV should compare literals just fine. This should be good. All right, so that's our first production. If we're looking at just an identifier and the identifier happens to match the thing we're looking for, as far as we're concerned, it occurs free. So I'm just going to return whether or not these two are the same symbol. Okay? Second production. How do we detect the second production? The second production is a list that starts with a lambda. Now, my other two productions both are lists, correct? So I know that if I'm not just a symbol, I must be a list that at least has a car. So now I can ask the question, if EQ car LCE lambda, that is to say I am looking at a lambda calculus expression that follows production number 2 of our grammar. This guy right here. The one whose car of the list is the word lambda. Make sense? If that's the case, now I need to determine whether or not S occurs in the rest. So that is the lambda calculus expression portion of this guy, along with what variables are bound in that environment. So this is where things, what I want us to start seeing here is our need for a variable environment. So when I have to ask the question, so we're going to write it here first. If I know I'm dealing with production 2, then I want to call occurs free, passing it the same S as we had before, and passing it the lambda calculus expression associated with this production. So the car is this guy, the catter is this guy, the CADDR is this guy, right? This is the car, this is the car of the cooter, this is the car of the cooter cooter.
Say that 10 times fast.
All right, so now I'm asking the question whether S occurs free in this lambda calculus expression. But we have an issue. Because I'm in production 2, here, a variable was just bound. It might not be the variable that we're looking for, okay? But a variable indeed was just bound. Therefore, if I'm going to call occurs free again, I need to find out if this guy was bound in the first place. I need to be aware of it. So somewhere I need to keep track of what variables were bound. Because later on, I'm going to what? I'm going to have a situation where I'm looking at an identifier and I see that it occurs. And now I'm going to wonder to myself, just like we did back here, well, as far as I'm concerned right here, it occurs, but I really don't have the given information I need to determine whether it's actually bound by the powers that be. In my little world here, it occurs and that's all I can say. The next guy up is in charge of what was bound. All right? So a variable can only occur free if A, it occurs, has to be there to begin with, and it only occurs in this production right here. Okay, so it has to be, it only occurs free if it's in that production, it only occurs if it's in that production number 1 right there. Then it only occurs free if it's also not bound within the current scope. That make sense? So if I return true that it occurs, and I want it to ultimately boil down to false for occurring free if it's bound, what can I do here? Go ahead.
Can you create a list and pass it into the occurs free function?
I was hoping you'd say that. You absolutely could, but we're not going to. But you're way ahead of the curve. Because certainly we're going to be very interested. There's two sides to that coin. You're saying let's create a list of all the variables that are bound in the current scope, right? Sure, yeah, we can do that. We only really need that though later on when we actually go to resolve variables. Really right now we just need to know whether or not it's bound. How do we know whether S is bound in the current identifier? Check the CAADR. That's a fun one, right? The car of the cooter. That gives us this identifier, the CAADR. So if that identifier matches, if that guy matches the symbol that we're looking for, then the symbol we're looking for occurs the symbol we're looking for is bound. We don't know whether it occurs yet, but we know that it is bound. And we need to somehow pass this information along the recursive call so that we have access to it. Okay, so if I know that it occurs here, that guy is only going to ultimately return true from occurs free if it also is not bound. Correct? So if this is true that it occurs, in order for it to be, the whole thing to be true, we must have another true here that only boils down to true if it's not bound. So can't I do something like this? And not EQ S let me just leave it at that for right now. So if I'm dealing with production number 2, then I'm going to return the AND function applied to the Boolean value returned by checking to see if it is true that S is not equal to the identifier being bound here.
Can you have multiple identifiers being bound?
Nope. If you look at the lambda calculus expression, it's a single identifier in this version. Coming soon to a theater near you. This guy's going to get a little bit more complex, but so that's coming up. Then we might need to do some mapping stuff. All right, so something for you to dream about. All right, so we're going to AND whether or not this guy's bound, but specifically the truth as to whether it's not bound. Because we're ANDing it, we want it to be true if it's not bound. So that if it occurs, we have a true and a true, which boils down to true. Make sense? If it is bound and it occurs, then it's going to be a false and a true, which is a false. Wait a minute. Does that occur free? Let's think about the possibilities here. It could be, as we currently have it written, if it's bound and occurs, it would be false, let's see, be and false. That's the not equal to this. So if it is equal to it, if it is bound, that will boil down to false. And then our thing up here says return true if it occurs. So if it occurs and is not bound, that's going to be true. So this whole thing boils down to false. Is that what we wanted to? Is that what we wanted to do? So that's if it is. That's if it is not bound, right? But it does occur. If it is bound, we're going to say if this guy is equal to this guy, that's true. Not true. Actually, hold on. This will be not bound is true. Occurs is true. That will be true. So that's the way we currently have it written. That's where the not comes in. So this says not bound. That is to say, if S and this value are not the same value, the identifier is not the symbol we're looking for. Okay, if that's a true statement, it's not the same. That's what this whole thing says. So this says, are they the same? If the answer is no, it's false. False flips to true with a not. That gets us our true. So this says not bound. NB, not bound. Okay? This guy says does occur. So if it's not bound and it does occur, it should return true for occurs free. If it is bound and it does occur, in that particular case, it would actually not occur free. It occurs, but it actually occurs bound in that case. That's our false. If it's not bound, but also does not occur, then it would certainly not occur free. It has to occur first in order to occur free, whether it's bound or not, right? Finally, if it is not bound, and realistically, whether it's not bound or not, it's going to be false coming out of here, and it does occur, well, it doesn't occur would be the last one, and it doesn't occur, this whole thing is false. Doesn't occur, doesn't matter whether it was a bound or not. In this case, it wasn't bound, but it didn't occur either, so can't occur free or bound if it doesn't occur. Make sense? All right, so that's where this guy comes in. So we're really stringing together a bunch of ands in order to build up a Boolean expression that will boil down to the correct answer, without actually keeping track of the variables that are bound or not. Later on, so the problem here is that now we can determine whether variables occur free or occur bound, but we don't necessarily have a list, as Josh pointed out. We don't have a list of the variables that are bound. And more importantly, later on, variables that are bound typically also have values associated with them. So this is where we need to start building up a data structure for representing variable environments. Okay, where a variable environment is going to be a collection of name value pairs, probably stored in a hierarchical collection of scopes. Sort of kind of at the super high level make a little bit of sense about what we eventually might want. All right. So that's our proof for this guy for our second production. Third production. Okay, third production is when we have a list containing two lambda calculus expressions. And we want occurs free to return true if the symbol occurs free in either of those, right? So we're going to use an or. So we're going to return, so now we have our else, or,
Don't you need another parentheses in front of else?
I don't think so. No, this is the syntax for cons.
The only reason you need one for the other one is because you're asking.
This is the Boolean expression, this part.
Yeah.
So else replaces that.
Else is in a,
No, it's part of the con.
Okay.
Yeah, it's part of, it's the, if you think about the cars and the cooters, it's the, The CADDR. CADDAR. Yeah, that one. All right, so else we're going to call the OR function, passing it occurs free on S and the car of LCE. Curse, I get it. Along with occurs free on the catter of LCE. Make sense? So let's test. So there's our true, the first one.
You don't pick up, makes that.
Huh?
Okay, I guess you're doing it like this.
Yeah. Oh, you want me to? Yeah, it's not gonna look right to do it the other way. It should be false. Let's go down to one of our crazy ones here. It came out to true. Make sense? All right, so that's occurs free, but with the caveat that we do not actually have a list of variables that are bound. We just get an accurate description of production one having variables that occur free or bound. So now how would I convert occurs free into occurs bound? Let me ask you this first. Is occurs bound the same thing as not occurs free?
No. Still has to occur.
Occurs free requires that it occurs, just like occurs bound requires that it occurs. But we can't just use the not because there's multiple reasons we could get a false out of occurs free. There's multiple, well, not multiple reasons we can get a true, but multiple reasons we can get a false out of it. So not occurs bound doesn't help us. Or I'm sorry, not occurs free doesn't help us in the implementation of occurs bound all the time. Intent. All right, so we're going to write occurs bound now. So define occurs bound. And this guy's going to take in a lambda, S, and an LCE. And we're going to have our con for building up our productions. So we start to see a structure here again. Whenever we have a grammar given to us that has multiple productions, we can use a con for representing each of those productions. It's going to be a very helpful structure moving forward. All right. So
does occurs bound return false if it only occurs free?
huh? I mean, if it only occurs free.
If it occurs free, does it
If it does occur free in a lambda calculus expression, that does not necessarily mean that it doesn't also occur bound in a lambda calculus expression. Because we could have this production, and maybe it occurs free on this side and occurs bound on this side. So in that particular case, occurs free and occurs bound would both return true for that lambda calculus expression. Does that make sense? Okay. Now, my hope is that at least half of you are feeling at least somewhat lost. Is that a fair assessment? Like, what are you, stupid? Okay. This is heady stuff. Right? So that's why you want to spend a bunch of time in your homework trying to understand this stuff. Go back and watch the videos to help put you to sleep at night, that kind of stuff. Yeah. So I just want to encourage you to, with the idea that you are, I don't know, yeah, I would say you're supposed to, a majority of you should be feeling like this is not horribly above your head, but floating up there just almost like out of reach, but you feel like you can kind of tip it. Right? You can almost get at it. So you're grabbing little pieces of it. That's where you should be. Okay? If you're like completely lost, like what's car do again? That's not where you should be. All right, it's not where you should be.
I can't reach
Does
over
it
and
drive
grab
the
the
Lambda?
Huh?
It drives the Lambda, right? Around,
Drives-
so it goes to the car, the cooler. It's like a limousine service.
Exactly.
It's like Uber, but better.
Let's see.
Uber stole your idea.
All right, so what time is this class over? 25, right? All right, we got plenty of time. All right, so occurs bound. Again, we're going to build up our productions. So if we have our, let's just steal this first production here. We'll modify it as necessary. So if we're looking at a symbol, we're looking at production 1. If you were to tell me in English what this line returns, what would you say? That entire line is testing for what? Well, yeah, it's true. It does boil down to a true or false. It is a Boolean expression. What's it saying? What are we really testing here?
The symbol you gave is the lambda expression.
We're checking to see if it occurs.
Yeah.
Okay, this is our one-stop shop for does the symbol occur? This guy is completely dumb to whether or not it's bound or free. All this guy tests for is whether it actually occurs. Okay? Whether we're writing occurs free or occurs bound, knowing whether or not it occurs is a very important piece. Agreed? Okay, so we're not going to touch this. This guy does his job. Do you occur? Yes, I'll let him know. All right. How we use that information up above is going to be maybe possibly different. So let's take our second production here.
Doesn't that give you a true?
Yeah, this will boil down to true if it does occur. False otherwise.
But you're trying to figure out if it occurs bound.
Yeah, but all this piece does here is whether or not it occurs. And all he can do is pass the information up to his supervisor, whoever called him, and let him know, yeah, he's here. Okay? You do with that information whatever you will. Make sense? Up here, we decided to do this whole and structure dealy flippy. Okay? So now we'll go to this production. And this production says if we're dealing with production 2, that is, it's a lambda calculus expression whose car is lambda. If that's the case, we need to do the stuff associated with that production. And it just so happens that this is the only production where variables can become bound by that single identifier. All right? How do we modify the result of our occurs free here to make it work for occurs bound? And I gave you a hint a few minutes ago. Go ahead.
Remove the knot.
Okay, you want to start off by removing the knot? All right, so here, let's let me steal most of this. All right, so you want to take that guy off, like that.
I need to take a parenthesis on that same line.
I did. I took a parenthesis off. Oh, you mean this line here?
Yeah.
Yeah. So I actually took the parenthesis off the wrong place. Thank you. It's testing you. Does this work? I did say I gave you a hint. So, it occurs bound if what's true? It occurs bound if, first of all, it is bound here. And second of all, it does what? You want to know whether it occurs. How do we know whether it occurs?
It's the
You know if it occurs from the first production?
well, you have to go to.
Or-
You have to,
Can I just, the real question is, can I just call occurs bound?
No. Oh yeah, because you have the same thing.
Really? Remember we talked about breaking problems down to their individual little parts. So what we're going to do next time is we're going to write a function just called occurs. Okay, and it's going to simplify our mentality for this, because what we'll be able to do is we're going to be able to say something like this. Okay, well, it's bound. So if it's bound and it occurs, then it occurs bound. If it's bound, or I'm sorry, if it's not bound and it occurs, then it's bound, then it occurs free. So by writing a helper function called occurs that only returns true under this very first production, we can make the whole thing work. Make sense? And that will make it make a lot more logical sense and be a little bit closer to the top of our head. All right, I will see everybody on Tuesday. Next homework assignment is already up. Good luck and Godspeed.